Hi there. Everybody pizzaed up and everything, everybody with drinks? Good stuff. All right. So today I'm going to talk about streaming data platforms. I might be, you might accuse me of overusing some buzzwords. So I'm going to try to also explain what that actually is, a streaming data platform, and how we do that today. And in order to do that, we want to talk about what data platforms now actually are, what they actually do, like in real life in most corporations and most enterprises. Well, it's usually just a bunch of like scripts that run, let's say an export thing, right? So let's say we want to dump some data and put it somewhere from a live database, right? Let's assume for a minute you have some production database in Oracle or something, and you want to do something with the data. Well, the standard approach is to say, okay, we're going to just generate a script and we're going to export that stuff and put it on a file share on an S3 bucket or FTP server, right? If you're a bit more sophisticated and you have some engineering power in the corporation, or you might also have just an HTTP endpoint, and then you just pull that HTTP endpoint and you get the dump, right? The problem with that is integration is difficult, right? Specifically because in order to get the data, you need to have a scheduling that is somehow synchronized, right? You need to make sure that if you run that export job at 3 a.m., that your consumers know that export job runs at 3 a.m. and completes at 3 a.m. You need to basically coordinate a lot of stuff. And that means that those data flows require a lot of orchestration. You need to make sure, the data dump was generated successfully. We're not getting yesterday's data, but we're getting today's data, and we can do something about it, and it's sort of fresh. But while you're processing that dump, right, and you're doing stuff with it, you're missing all the updates that happen afterwards. So that leads to basically another problem, right? You have everything's designed for ETL, right? ETL stands for extraction, transformation, and loading, and you have a data repository in a data warehouse, or maybe in a data lake, like a standard big data Hadoop kind of lake that was established. And it's actually used to be, like 10 years ago, really the coolest and most modern thing ever. But everything is still batch, right? So that limits the scope of things that you can do with that platform, because essentially the focus of those data platforms is basically fulfilling reporting needs. Not that they're not unimportant. A lot of companies need to have proper intelligence and insights, but what you can do with that platform is limited to exactly that. So business intelligence, reporting. And the other problem is, since we're using batch cycles and scheduling, everything is pretty much after the fact, right? The delivery is dependent on periodic schedules. And lastly, those platforms are specifically optimized for broad but few queries, right? So everybody who's basically tried to execute a query, a simple query on a data platform, will always wonder, why the hell is this so slow, right? And if you actually execute a lot of those queries, first of all, somebody's basically going to ring you and say, hey, the cost of running these queries is going through the roof, especially if you're using one of those pay-per-use on-demand managed service query engines. And you might not even get results. And on top of it, because we have a lot of different, let's say, periodic scheduled batch ingestion pipelines, we basically run into the problem of the data swamp. The data swamp is essentially like a repository where everybody loads their stuff in and nobody knows really where the stuff comes from. I mean, we have a client, for instance, that were telling us, we're basically processing the stuff in our lake, but sometimes we don't even know whether the record that we're looking at is something that we actually saw 2 weeks ago, enriched, and because it was consumed by another system that sent it back to an upstream system, we're seeing that data set again with our changes in it. So lineage is impossible, and you don't really know where the stuff comes from, and you have a lot of duplicates. And on top of it, everything's always behind the source, right? The source system emits something, and you're dependent on that batch cycle to see to see the change. And lastly, duplicates. We can see multiple versions of the same data set. That's a huge problem. So data lineage and swampifying your data lake is a huge challenge. Now, if we look at, let's say, the other side of things, notably the microservice or service landscape, essentially the upstream systems in front of the data lake. Well, these guys, when they actually want to consume something from the data lake, they basically have to do something that's called reverse ETL, right? So, they emitted the data, it went into the data lake, it was transformed and processed, and there's reporting stuff and whatever, and now they want to consume something. Well, they have to transform it back into their own representation. And there's a lot of data synchronization overhead, and usually developers have to invest a lot of time to sort and interpret back the data that they're getting. Orchestration is required, and it's a huge overhead. And lastly, because you need to do all of that stuff, integrating with data platforms is costly and problematic. So now when we're looking at everything, you're just putting the microservices, like the upstream systems, and the data platforms in their current incarnation, it's a huge mess. An enormous orchestration overhead. There's a lot of bespoke ETL, so you need to transform the stuff from one representation to the other, and doing some reverse ETL as well. And you have the problem of ensuring that you're not looking at cyclical data relationship problems. It's very, very messy. So what if, right? What if we could actually just magically solve this problem and remove all the orchestration overhead? What if we could just basically think about data products or data platforms just like we think about microservices, right? What if we could just basically say that there's a domain to a specific service with a clear-cut data input and data output with, let's say, the kind of domain-driven design thinking that we often see in microservices, not always, but often. It's like recommended to build microservices that way. And you can just basically do the same thing in data land. And what if we could also just use the same approach to bridge the operations or the enterprise or service landscape and the analytical landscape, right? Some of you might just think, hey, wait a minute, aren't we just going full circle back to relational databases where we basically created reports off a relational database with an application in front? A bit, right? But not quite. And lastly, what if we could get rid of ETL altogether? Right? Just not think about having a separate ingestion or bespoke ingestion process that extracts, transforms, and loads the data, or ELT, or whatever combination of those letters you want to think of, right? So now, what that means is that we're just thinking about streaming data platforms as data products. Okay, buzzword, true, right? It is a buzzword. But the data product idea is just basically a new label for a different way of thinking about data. So what does that actually mean? Right? It means that we're trying, in this architectural approach, to unify the streaming idea, right, which gives us near real-time updates, and storing the data. Because for now, when we think about, let's say, some application landscapes, you have near real-time processing, especially in the upstream services, when you're basically handling user input, credit card verifications, payment transactions, whatever, right? All of that happens up front, and then you just dump the data somewhere, and the data platform stores all of that, and then you can do analytics on top of it. But there's a separation between the two. Now, what we're looking at is specifically saying, okay, we don't have to separate those two. We can actually bridge them and implement a data product that does both at the same time. So you can actually basically cater to the needs of a front-loaded or upstream application and serve the analytical workloads as well. just in one, right? So data product is a service that owns a single domain. So instead of actually just putting everything into one big data lake and saying this is unstructured data and we'll just post-process it later with a Flink job or a Spark job, specifically a Spark job or MapReduce or whatever, what have you, we could just basically say there's a service, it owns everything that has to do with, let's say, payment transactions, right? That's the domain. And what it also does, it basically presents data for business and analytical workloads. So it basically can answer to any queries that the business has in terms of reporting. Let's say, give me all the, like an aggregate representation of all the payment transactions that happened in, let's say, the southeast of England, right? In our shops, for instance. And at the same time, also process incoming data payment transactions from terminals that we operate. Right? So, and lastly, when we have those data products with the different domains, we basically use another aspect of instead of having a data lake, we basically have a mesh of smaller data lakes, the data products, and we organize them in a mesh structure rather than in one big bucket of everything. So when we're thinking about that, of data products as an idea, we're thinking about decentralized ownership, right? So there's a clear domain boundary, which is also an idea that comes from microservices, where you basically have clear boundaries for different domains and entities. You're source agnostic. So essentially, it doesn't really matter whether you're looking at operational and analytical data sets. It's self-contained. So it basically says, I have raw data in my data product, and I have enriched data sets in my data product with different application scopes and answers. And lastly, we have standardized interfaces. So we can basically answer queries asynchronous and synchronous queries. So you can basically do lookups on that data product, but also subscribe to changes through an asynchronous pipe. So what that requires is an approach that we call shift left. Shift left means that you're pushing the processing requirements from downstream, right? Like we used to do. We used to accept we're getting multiple raw data sources from X, Y, and Z, and we're then just interpreting that data set, merging, joining, processing, aggregating further downstream, and then creating a bespoke product. Rather than doing that, we just push all of those requirements and that processing requirement, enrichment requirement, and cleansing requirement further upstream. So basically, if you look from left to right, on the left you have upstream, on the right you have downstream. So you just push that stuff further to the left, which basically means that you also remove the requirement of doing interpretation and cleansing further downstream. And that also comes with another requirement. When you do shift left, you have to have clear data contracts. So a data product is a service level implementation of the medallion pattern. Are you familiar with the medallion pattern, like bronze, silver, gold? Good. You have a question? Oh, yeah, okay, good. Sorry, fine. I'll take questions afterwards. Thank you. So specifically, when we're now thinking about how these data products interact and how you access the data, we differentiate between a continuous delivery to a destination, which is a stream of events. So we're talking a Kafka, right? So we just basically have an input that is a Kafka topic and an output that's also a Kafka topic. So you basically just continuously deliver the stuff as updates and update events. And you also provide consumable endpoints either as a subscription for your consumers or as a query API. So you basically have an HTTP interface that you can query and say, okay, I want to have the latest representation of the snapshot of entity X, Y, and Z. All of that is guarded by a very clear data contract. So you have a clear interface of what the structure and the schema of the input data is and what the outputs are. So lastly, when we're looking at the technical implementation, we're looking at building blocks for data products. And there are like obvious contenders. It's not a must-have, but let's say that's usually how things are done because of the excellent support that you get. Obviously, this is a Kafka meetup, big surprise, Apache Kafka. It's basically the de facto standard for message brokering. Obviously, you can also think about Red Panda and other implementations, but we're talking Kafka protocol here. In data platform land, integration is key. So one of the big advantages of the Kafka platform and one of the selling arguments was not necessarily the excellent brokering platform and all the let's say the semantics that come with a brokering platform, but the real killer in terms of pushing Kafka into many enterprises was Kafka Connect. Kafka Connect gives us the ability to integrate hundreds of different system types into a platform with a uniform interface. It is one of the most brilliant ideas that Confluent came up with to push Kafka Connect into the enterprises. It also makes it much easier to integrate with legacy systems. So when we're thinking about SAP, Oracle, other ERP systems, or even Salesforce or whatever, just being able to subscribe to an event stream from these upstream systems without having to implement anything is a huge game changer. Of course, once we basically collect and get data into a data product, we need to do some processing with it. So obviously we have a few different choices. You have frameworks, such as Kafka Stream, Spark, Flink, Quix for different languages. Zio, for instance, is Scala. Quix is a Python framework. So you have different choices in terms of stream processing that are built around the concept of having an input stream, doing some stream-oriented transformations on top of it, and emitting an output stream. You also need the ability to query these data products. So you basically think about Rising Wave, for instance, or Materialize, which are streaming SQL engine implementations that give you the ability to query a stream with standard SQL. And lastly, Apache Iceberg, which is the de facto standard for open table formats. Well, that is important, we'll talk about in terms of fulfilling the full requirements of a data product. So when we're looking at a data service architecture, the data product, we're unifying batch and streaming into a single architectural platform, right? Which basically gives us the ability to serve real-time subscriptions and lookups. So essentially you have one product implementation using those building blocks, give us the ability to process and subscribe to streams, do transformation in real time, but also provide an interface for lookups and snapshot delivery in one single service implementation. So looking at Kafka, we use that as the de facto streaming implementation for data streaming and data in motion platforms with a combination of Kafka Connect, as we discussed earlier, which is like the usual choice. But we need to snapshot that stuff somewhere, right? So essentially when we're basically processing an incoming stream, an incoming data stream, we need to be able to say, okay, whilst I'm processing, I need to store what I processed. So we basically say an event that was transformed, aggregated within the data platform is also stored in situ, right? In order to do that, instead of storing stuff in the database, we just basically use open table formats, which gives us the ability to do merge operations and upsert operations on a cheap store with very flexible transformation capabilities. So in conjunction with a Metastore, gives us the ability to use a data lake approach within a service. We're looking at in-stream processing. So obviously we have a few choices here. For simple implementations, we can use things like KSQL DB or KSQL to just basically do some projections within one stream to the other. But if we do some more, let's say, more complex processing, we're looking at things like Spark or Flink or Quix, right? Essentially just the ability to do some in-stream aggregation with, let's say, like near real-time processing. But that is just part of the story, because obviously being able to process and aggregate stuff requires also the ability to transform the data within the data product. And that's what we call basically the ability to do a single or multiple data projections. So essentially, if you're looking at an incoming stream, you're processing the data and you want to transform it to something else. Let's say, for instance, you're looking at billing, for instance. Billing is usually just the combination of invoice items and then address and different entities, and you just subscribe to all those streams. And within the stream processing, you want to create billing records, and you combine those, and you project different data sources in stream into an outgoing stream of combined and joined data. So that's where we basically say the data product is computing a materialized view representation of several sources at once. So let's assume for a minute that you're getting, let's say, purchase basket or whatever, like let's say it's commerce, and you have like invoice items, and you want to generate invoices that are sent to the customer. You want to do that as quickly as possible. Well, you need to do a few computations to create an invoice, right? You need to know the basket, the order items, the inventory numbers, the prices, availability, and then you have to look up customer stuff, and you have to look up addresses. So you're basically querying either static data sets, right, that are in repositories that you can query, or you're basically processing streams, and you're doing the combination of both within a data product, and that results in a projected new entity that you create, which is the billing record that contains all these data sets, and then it goes out either into a stream or into a snapshot representation that can be called by a downstream system. And so essentially, the principle of view dematerialization gives us the ability to combine multiple data sources regardless of where they come from, right? And what system, what upstream system is responsible for that. We could basically think about, again, the billing example, we're getting some stuff from Salesforce, for instance, and some other stuff from an ERP system. Right? And we're creating a billing record that goes to an accounting system. So generally, we're thinking about source agnostic computation of a stream-oriented view. That's why we call it a materialized view. Everyone who has basically done a lot of stuff with relational databases will know that that is a thing in some databases where you can basically say, I have a view, but in order to make it performant, I materialize it into a table. Well, that's a bit the idea behind this, except that we do that in stream. And in order to do view materialization, there are a few options, right? One is Flink. Flink is quite potent at view materialization computation, especially Flink SQL, because it gives us the ability to actually express a materialized view as SQL. And that also gives us the ability to snapshot directly to Iceberg and Delta Lake, and also Pymon, which is their Fluss product. But let's say Flink is a difficult thing to adopt, right? So there's a lot of overhead in adopting Flink, specifically because it's such a powerful framework. There are easier options. One of them that we use in our projects is Rising Wave. Rising Wave is a streaming-oriented database that uses Postgres syntax to do exactly that kind of view materialization computation, and gives us the ability also to expose the output to different formats at the same time. So you could basically say, okay, the materialized view that I'm exposing here is also snapshotted to Snowflake, for instance, and S3, and Iceberg, and Kafka. So you can basically say that output goes into different downstream systems. So it's quite powerful in terms of expressing your transformation and streaming transformation needs in data products as SQL. So it simplifies also the implementation overhead. So tying all of that together, data product is a service that owns a domain and provides data projection capabilities. So it basically does computation, and the computational result, that's where we think about the medallion architecture as the gold layer, gives us the ability to project slightly different versions of the same data for the downstream consumers. And it supports real-time lookups and subscriptions. So when we're thinking about a data product, we're thinking about duality, right? So there's a duality in terms of streaming and of data repository. The duality means that you have streaming first, right? So everything is a stream, everything is computed in near real time, and we subscribe to updates regardless of where they come from, at what time they come from. We project those streams and aggregate those streams, and we snapshot the streams back into a data repository that can be looked up. So that duality gives us the ability to think about streams and use streams as if they were static, quote unquote, CRUD applications. And it gives us also the ability to choose different, with this pattern, we choose different implementations as well. You can implement a data product with Flink, another with Rising Wave, another with Spark, and another just as a microservice implementation with let's say the framework of choice. So generally, when we're looking at an overview, you basically get a data mesh with Kafka in the middle, right? And multiple data products with different implementations, but all backed by Iceberg in their as their repositories, and with the ability to service multiple needs and multiple downstream systems. So that concludes my talk today about data streaming platforms and, let's say, the convergence of microservice design and data platforms. And I'm happy to take questions.
When would you use Flink over Rising Wave? Is it just the complexity of the queries, or is it like the maturity of the teams?
Yeah, I think like one good. Let's in the different projects that we have, we believe that 80% of the needs is just simple aggregation and projection, right? So just let's say the simple use cases, you have a generic implementation of a data set, let's say telematics, right? In e-mobility, you have like, let's say a generic telematics schema, and you have like 4 or 5 different providers that have all their own interpretation of what that is. And you want to transform that into your format, your standardized format. You can express that very simply with SQL, right? Just, map different fields to another. You just explain that in SQL statement and bang, you're done, right? Coding that in an application is a lot of work and unnecessary work, right? And in our experience, 80% of the tasks that we have in data platforms are around that kind of projection work. Of course, there are some more complex computations that need to be done, and you can't do them that easily in Rising Wave. Of course, you can just use UDFs, right? User-defined functions to do some more complex computation, but that's not necessarily as performant. So generally, it's not an either or, but an and, right? So let's say for the complex stuff, you'd basically choose something like Spark or Flink. And for, let's say, the majority of the computational needs, you can use, if you're using Flink, you might want to consider Flink SQL, which is also quite powerful, or Rising Wave instead, right? Please.
I have a question from the data product manager perspective. Right?
Yes.
In terms of organizational level, I understand the two different use cases. But in terms of personas, could you give me a use case where it could be both streaming as well as extract simultaneously? Because I could not come up with one.
Well, there's actually one that is quite common in manufacturing, and that is digital twin, right? Digital twin is a huge piece of regulatory requirements that every manufacturer has to somehow fulfill, right? It starts with like rubber stamping the assets, digital assets and non-digital assets. And that stuff is actually benefits from that duality approach, because in digital twins, you need to be able to, let's say, query where the asset currently is, right? And just get that. Okay, so well, we've delivered this piece of machinery somewhere. We need to know where it is. Like you just query that. But if you have some kind of legal requirement, you need to also do an extraction of the history, right? And the event source history of that data, of that asset or multiple assets or other like more complex queries. So that basically reflects that kind of reporting and forensics need that comes with, let's say, typical data lake implementations, as well as like the day-to-day query of, where is my stuff right now, right? So that is a good, like a typical use case for that in manufacturing. Yes, please.
So my question is also sort of related to data products. So in terms of the operational aspects of it, so you mentioned that a lot of it's going to be shifting left. So how exactly, like how would that sort of in real life translate into like requests and requests for like new reports, new changes and things like that? Because one of the reasons why we have redundancies in our data is because you need to deliver something really quickly, and because you have that flexibility sort of downstream, you can sort of cut and dice the data anyhow. But now that's moving towards a bit more centralized or decentralized sort of format. I'm not sure what exactly it is actually, so if you can just touch on that.
Yeah, precisely. And that's an excellent question. I really like it because it really pinpoints the problem, right? We basically accept duplication and batch processes because it's so much harder to get others to do something for us, right? That's the actual problem, right? And the interesting thing about data products is that the domain responsibility is with a specific team, right? Of course. So at first you'd think, oh my God, there's so much friction. We can only get the data from them, these guys. They're never going to give us the data like we want to have it. Well, that is not true, because by making projection easy and cheap, right, it is actually quite easy to say, hey, we need the data delivery in a specific format. This is our schema. Right? And you get it because it's just SQL, right? Just say, okay, this is SQL. And in fact, that reflects very much how people discuss requirements between different units, right? Especially large corporations we work with, they tend to describe their data contracts as SQL, right? I've seen that, where they say, this is our model, this is how we want to have it, and they just shift the requirement specification. And then it's sort of like, okay, we're going to give you a dump. But instead of doing that, they could just execute the SQL that just delivered. And then you get the projection right away as you want it, as you need it in your product. Because everybody can basically say, we need a gold layer representation of that data set. Makes it easier also in the interaction with different units. Yes, please.
Yeah, I also have a question about shift left approach, because usually you want to keep the raw data for multiple purposes. One is regulatory, sometimes you need to provide the exact data. Mm-hmm. And the second thing is, if you need to recompute data, you found an issue in upstream.
Yeah.
How are you gonna?
The thing is that we're not doing away with raw data altogether. We're not, right? The only thing is that we're basically saying a data product, the implementation of a medallion architecture happens within the data product. So the data product has a cheap storage. It has like iceberg tables. You can just dump the raw data internally and do the computation and basically do the typical bronze, silver, gold computation within the boundaries of the data product. Right? So you can do recomputation, and the benefit of doing that is that the recomputation happens independently of everyone else, right? When we're trying to do recomputations in like classic present day data lakes, well, there's hell to pay because you have to coordinate and say, oh, I'm just going to recompute this bit but not touch that, and maybe there is some lineage problem. That's the issue, right? So, yeah. Yes, please.
CEO of a company that's going from the initial example, the data platform with all those issues. How do I make the first steps towards more of like the data product domain specific organization? Seems like it's got to go top down, right? Maybe a big jump even. What's like the first steps?
Well, our recommendation That's funny because we often have that question, right? Our recommendation is to use the strangulation pattern, right? The strangulation pattern, right? So instead of basically saying, oh, we're just going to wholesale migrate everything at once, that doesn't work. You have to understand, you basically look at your structure, you identify the pain points where you have like real issues of computation and of delays. And then you say, I'm going to look at exactly that, right? And I'm going to migrate that data product first and chisel it out of the current data lake structure and basically move it to the new approach. And over time, basically everything migrates, right? Because you go one product after the other.
There's an organizational change that has to happen along with that too? Or?
Yeah, to a certain extent. I mean, that's the same reverse Conway's law kind of approach that we see in microservice migration projects, where basically instead of having siloed organizations with, let's say, an organizational pattern that's oriented or structured around capabilities, you basically shift the organization towards ownership of a specific service or domain, right? So that needs to happen. Because otherwise you're invariably going to go back to centralized siloed management. That's a prerequisite, but that's probably the only thing that really needs to happen. Oh, yes, please.
So are there any sort of cost savings or disadvantages to using this new sort of data?
Well, let's put it this way. In continental Europe, with our clients, we have like the kind of recession thinking, right? So they all say, oh, we can't invest in new platforms because, it's going to be, we don't have any budgets, etc. So the argument is, okay, we're doing a zero-sum investment game here, right? So we're going to do the implementation and finance the implementation off the savings that you get. And the potential is enormous, right? Because if you stop for a minute and think about what we do here, right? We're doing a lot of redundant bullshit, right? Like you're just dumping stuff and reprocessing and dumping it again. Just the operational side of things is insane. And we're not talking about all the humans that have to do something about it. So in our experience, it usually finances itself. We have one use case where we basically we slashed the operational, like just the AWS and other service bill by 60%, right? Just by doing away with expensive snowpipe transformations, right? Just went away, right? So that slashed $30,000 in one go just because it just went away. So you have substantial cost savings by choosing this approach. All right, thank you very much.
Thank you, Eric. We'll take a 5-minute break, 10-minute break, get some pizza and beer, and then we'll come back for the next speaker. Thank you.